In section 4 of chapter 6, we're going to be bringing together all of the topics that we have been discussing thus far. We're going to bring back the removable and non-removable discontinuities, ergo the point discontinuities and the vertical asymptotes. We're also going to be talking about and utilizing horizontal asymptotes. We're going to be adding an additional bit on top of that and also stating the domain using interval notation. But we're going to be throwing that all on a graph and sketching an idea of what the graph should/could look like. Again, as a little repeat of what I said previously. This is kind of a prelude chapter. You're going to continue this topic in pre-calculus and calculus. You do not yet have all the tools necessary to fully graph these types of functions. However, we as mathematicians feel that it's unfair for you to go through that entire huge chapter of topics as if it was brand new in that calculus class, because that would make it way too cumbersome. So we're just doing the initial stages now. It'll get fleshed out as the year progresses. I feel like I'm just going to do a problem. I got two functions I'm going to graph. The first one is relatively straightforward, or at least as straightforward as graphing rationals can be. The second one has a little bit of a twist to it. So problem number one, I have f of x is equal to the quantity 2x cubed minus 12x squared minus 32x quantity divided by the quantity of x cubed minus x squared minus 30x quantity. I am going to find the point of discontinuity, vertical asymptote, horizontal asymptote, the domain using interval notation, and then this last bit that I'll reveal at the end. All right, before I do any of that, I should probably factor this. The numerator, the 2x cubed minus 12x squared minus 32x, they are all divisible by 2 and x. So I'm going to do GCF. I'm going to factor out a 2x. That'll leave me with x squared minus 6x minus 16. All divided by. Denominator, all three terms are divisible by x. So I'm going to factor out an x. And that'll leave me with x squared minus x minus 30. All right, did GCF first. Next step, take those trinomials that are inside my parentheses, and I'm going to factor them. You can use whatever factoring technique you want. You can use the area model, diamond method, completing the square, quadratic formula, the TikTok method, the old school method. At this point, you can use whatever technique you want. I showed you the area model, but if you have a preferred technique that you learned somewhere else, go ahead and do that. But when you factor that, you're going to get x and x, 2 and 8, positive 2, negative 8. And then the denominator, that x is still on the outside. When you factor the trinomial in the parentheses, you'll get x and x, 5 and 6, positive 5, negative 6. Now that it's completely factored, I do like to have a special note that means x cannot be equal to 0, negative 5, or positive 6. Those are my discontinuities. I will label them right after this as to whether or not they're removable or non-removable. All right. These are all the calculations that you'll need to do. The rest of this is just interpretation and then planting those interpretations on the graph so you can see a visual representation of the original function f. So, without further ado, let's do the removable discontinuities, also referred to as the point discontinuities. Those are the discontinuities that would eliminate once you simplified the problem. The x on top and bottom would eliminate. Therefore, the discontinuity that came from it is considered removable. Next, I'm going to do the non-removable. These are also what are called the vertical asymptotes. They're the vertical dotted lines. So now I'm looking and seeing which ones remained. There was a negative 5 remaining and a 6 remaining. Those came from these two spots. So those are my non-removable discontinuities, aka my vertical asymptotes once I get to the graphing portion. Next, I'm going to be stating my horizontal asymptote. For the horizontal asymptote, I look at the problem before it was factored. I look at the original question that was given to me. I compare the power of the polynomial in the numerator with the power of the polynomial in the denominator. Look at the degrees. This is a third degree function on top, third degree function on bottom. Since they're the same, the horizontal asymptote will be at y equals a over b, where a is the leading coefficient for the polynomial in the numerator, and b is the leading coefficient in the polynomial in the denominator, which is a 1, because that's 1 times x cubed. So it would be y equals 2 over 1, which is just y equals 2. All right. I'm now going to list the domain of this function. I'm going to use interval notation, because interval notation is really useful when there are multiple stopgaps. We're going to go from negative infinity to infinity, and we're going to make stops at each of the discontinuities, regardless if they're removable or non-removable. So we're going to start at negative infinity. Our first discontinuity, the smallest one, is negative 5. And then we're going to take the union of that interval with the interval from negative 5 to our next smallest, which is 0. Then the union of that interval with 0 to our next one, which is 6. And then lastly, 6 to our infinity. And that is the domain of my function f. Here's the only part that is new. This is the part I alluded to earlier in the chapter. We never use these two pieces up top. We are today. These are going to tell us the x-intercepts, which if you think about it from an algebraic standpoint, kind of makes sense. X-intercepts are where a function hits on the x-axis. The one thing all x-intercepts have in common is that the y value is equal to 0. In order for this to be equal to 0, for a rational function, the numerator would have to be equal to 0. You'd have to have 0 divided by a number. The numerator will be 0 when these are 0. So that'll occur when x is negative 2 and when x is positive 8. These are all the attributes from the given calculations that we have done. This is going to be, for now, sufficient enough for us to start graphing these rational equations. All right. We will be doing the removable discontinuity last. You'll see why once we get to there. So my recommendation, do the non-removable, then the horizontal asymptote, then the x-intercepts, then we'll graph, and then we'll do the removables last. So the non-removable discontinuities, aka the vertical asymptotes, are at negative 5 and 6. 1, 2, 3, 4, 5. Here is my first vertical asymptote. The next one is at 6. 1, 2, 3, 4, 5, 6. All right, those are the locations that the graph is never, ever, ever going to touch. Next, the horizontal asymptote is at y equals 2. So we go up 2, and then we draw a horizontal dashed line. I do want to mention, while vertical asymptotes and horizontal asymptotes share the same name, they're both asymptotes, they behave differently. We will go over that in this specific problem. But vertical asymptotes and horizontal asymptotes, they look the same on the graph, they have the same name, and they largely behave the same way, but there are key characteristics that differentiate one from the other. All right, next I'm going to do the x-intercepts. The x-intercepts are at negative 2 and positive 8. 6, 7, 8. Now, this is enough information for me to graph. The vertical asymptotes separate the graph into sections. There's a section on the left, a section on the right, and there might be multiple, but in this case, there's just a single section in the middle. My recommendation, do the ends first, then do the middle last. So I'm going to go on the left side first. You have two options. Either the graph is going to start flat and go high, or it's going to start flat and go low. Those are the two options. As long as the horizontal asymptote is not on the x-axis, it is fairly intuitive as to which one to do. if it was on bottom, starting flat and going down, notice that if I want to trace that, I have to cross the x-axis. If I'm crossing the x-axis, when I found my x-intercepts, shouldn't I have found an x-intercept right here? Yeah. So if I want to start down here, I would have had to had an x-intercept. Because there is no x-intercept here, that means it needs to be on top. Oops, wrong color. Now let's look at the right side. It's either going to start flat and go high or end flat and go down. It is going to be on the lower side because I needed to go through this intercept. If it was up here, you could not go through the x-intercept. So if I want to go through this x-intercept, it's got to be down here. Therefore, it's going to look something like this. Now, for the parts that happen in the middle, here is how we go about doing this. For a large portion of this, it's going to feel a little bit like magic, but again, this concept will be explained more thoroughly once you understand the idea of what are called limits. If you look at this asymptote and where it came from, this asymptote is at -5. That came from this part of the rational equation. Because this is brought to the first power, most of the time they'll be brought to the first power. It's not a quadratic, it's not to the second power. What'll happen is, if this ended going up, it's going to start on the other side of the asymptote, appearing from the bottom. This asymptote here, which is at x equals 6, which came from this part of the rational equation. Because this is brought to the first power, the same pattern will emerge. It was going down on the right side of the asymptote, therefore it will go up on the left side of the asymptote. It skips sides. If that power is an even number, if that was an x minus 6 to the second power, they would both show up on the same side. So if this was an x minus 6 to the second power, if it started low here, it would start low here as well. So even powers, they start going in the same direction, odds they are split. Here's where it gets weird. This is one of the reasons why horizontal asymptotes are different than vertical asymptotes. When I graph this, it's going to look something like this. It's going to go across the horizontal asymptote. The difference between a vertical asymptote and a horizontal asymptote is vertical asymptotes, you are never allowed to touch them, ever. Horizontal asymptotes purely dictate what is called end behavior. In reality, the asymptote that is horizontal, it really only starts taking effect at the very ends of the graph. It doesn't really do anything in the middle. You can ignore it or you can respect it. It depends on the function. So in the middle, you don't have to act like there's a horizontal asymptote at all. The last thing I want us to do is I'm going to do the removable discontinuity. This one is at x equals 0. So I find where on my graph x would be 0, which is right here. And I'm going to put an open dot. And this is the graph of the rational equation f of x. In problem number 2, largely going to be the same. The main twist is that the horizontal asymptote is going to be on the x-axis, which means for our end kind of behaviors, we can't rely on x-intercepts to tell us how it's going to behave. So we have to come up with another way of doing it. The x-intercepts thing that I showed you, it works most of the time, except in these instances. And I like it because it's something you can do really quick and easy. The other way you can do it is a little bit more mentally time-consuming and taxing. So first step, I got to factor the top and bottom. That's going to turn to x plus 1. Can factor out of x. And then that'll turn to x plus 4 times x minus 3. There, factored really quick. That means x cannot be equal to 0, -4, or 3. Those are my discontinuities. I don't know yet if they're vertical asymptotes or point discontinuities. For that, I have to figure out if they are removable or non-removable? In this problem, none of them got removed. Therefore, for the removable, there are none. You need to put that. Do not leave it blank. I need to see that you state there aren't any discontinuities that are removable. For the non-removable, aka the vertical asymptotes, it's 0, -4, and 3. So there's one at 0, 1, 2, 3, -4. And 3. All right, next, horizontal asymptote. It's going to be y equals the power of the denominator, it's a 3rd degree. The power of the numerator, it's a 1st degree. It is bigger on bottom than it is on top in terms of the degree of the polynomials. Therefore, it's y equals 0. That is to say, it is the x-axis. Now remember, horizontal asymptotes largely are different than vertical asymptotes. They just dictate what happens at the ends of the graphs, not really what happens in the middle. So like intellectually, you can kind of think of it like the middle dotted sections. You can kind of like mentally erase those. They don't mean anything. It's just the ends. And then I can do the x-intercepts. The x-intercept is, there's only one of them, x equals -1, which is right here. There's my x-intercept. Okie doke. And then let's just do the domain for funsies. The domain is going to be -∞ to -4, union -4 to 0, union 0 to 3, union 3 to infinity. All right. We're still going to start at our extremes, what's happening on the left and the right side. But we don't have x-intercepts to go off of anymore because there aren't x-intercepts on the ends. So how do we go about doing it? Well, what I'd hope that you recognize is you've only got two options. Either the graph is going to start flat and go high, or it's going to start flat and go low. We've only got those two options. So what we're going to do is we're going to plug in a number to the left of that asymptote into the factored form of the function. Now here's the nice thing. We actually don't care what the value is. All we care about if it's above or below. We only care if the output is going to be positive or negative. That'll tell us which of the two it is. So what I do is I throw in a really, really large theoretical negative number that's all the way far to the left. If I throw in a really, really large negative number, like -10 billion, -10 billion plus 1, it's still negative whatever. It's still really, really negative. So the numerator would stay negative. I'll do this in like pink, I guess. So if I throw in a really, really large negative number, the top would remain negative, and the bottom would be a negative times a negative times a negative, which is also negative. So if I threw in a really, really large negative number, I would get a negative divided by a negative, which is positive. Therefore, really, really far to the left, it's going to be above the x-axis. Therefore, I have to graph above the x-axis. The way I do it on the right side is exactly the same. I throw in a really, really large positive value, like positive 10 billion. I'll do this one in, what color do I want? I don't have a whole lot. Orange? No, I already used orange. Let's do this. It's a slightly different version of like pinkish purple. If I throw in a really, really large positive number, a really large positive number plus 1 is going to stay positive. Divided by, this will be positive, this will be positive, this will be positive. Positive times a positive times a positive is positive. Positive divided by positive is positive. Therefore, on this side of the asymptote, it's going to have a positive y value, which means we're above it. So it is going to stay above the asymptote. Now the middle part's where, again, it gets a little tricky, a little funky. You need to look at each one of these asymptotes and ask yourself, is it an odd asymptote or an even asymptote? If they are even asymptotes, if you ended going up next to an even asymptote, you will start on the other side going up. If you ended going down, you go to the other side going down. They will match the same heights. Odd asymptotes are the ones that go on opposite directions. If you stopped going up, then when you go to the other side, you started on the negative infinity side. So in this problem, how do we determine if it's negative or positive? This asymptote came from the -4 discontinuity, which came from this part of the equation. This part of the equation is brought to the first power. They're normally brought to the first power. Very rarely will you see something that's brought to the second power. That power is odd, therefore that asymptote is odd. Since on the left side of that asymptote I was going up, when I go to the right side of the asymptote, I will be starting on the other side, going down. I'm going to have to go through this x-intercept. That means it's going to look something like this. Again, that's also an odd asymptote, so I'm going to go down. And because this other asymptote is also odd, I'm going to have to start going down here as well, which is why there is no x-intercept here, because on this side, it's going to go up, not touch the x-axis, and go back down here.